Today we're going to wrap up section 7.2. We're looking at something called continuously compounding interest. Okay, slightly different from what we did yesterday. Yesterday we learned about compound interest, and the more often it's compounded, the more money we'll make. So what would it mean if we said our interest was being compounded continuously? Well, if we're compounding continuously, it means we would compound an infinite number of times each year. So n would equal infinity. But we can't plug infinity into our equation. So mathematicians have created a new number. It's called e. It's referred to as the natural base. As x approaches infinity, this expression, which should look kind of familiar, because yesterday we talked about 1 plus r divided by n to the nt power. So it's very similar to that, 1 plus 1 over x to the x power. As this n or x value increases to infinity, this whole expression is going to approximate e. Okay? And e is basically 2.718. It's, again, a number kind of like pi, a decimal that keeps going, but it's about 2.718. So this gives rise to a new equation when interest is compounded continuously. Instead of the equation we had yesterday, which was a equals p times 1 plus r over n to the nt power, we are shifting now to this one. It says a of t, which is still our final amount, just like we had there. P is still principal. What changes is this piece right here. It turns into this. Okay? So our formula says we take our principal times e to the r times t power. Again, r is our interest rate and t is our time in years. So let's suppose we won a contest at the start of 5th grade that gave us $3,000 in an account that's paying 5% annual interest compounded continuously. How much will we have in the account when we enter high school 4 years later? And how much would we have after we graduate high school, which would be 8 years after we won this money? All right, so let's start out. Our first piece here, our principal. We were given $3,000. Our rate was 5%. Again, we're converting that to a decimal, 0.05. It's being compounded continuously. So we're going to use that e in our equation instead of an n. And then our time, we have two versions. The first one, they want us to look at what do we have 4 years after we won it. And our second one is what do we have 8 years after we won it. All right, so our formula here, our total amount is our principal, 3,000, times e to the power r times t. And our interest rate was 0.05, and our time for this first one we're going to say is 4 years. Okay? Then we're also going to figure out 3,000 times e to the 0.05 times 8. All right? So 4 years and 8 years. Let's look at our calculator here. So we had $3,000. Try to move this up a little bit here. All right, $3,000. Your E key is going to be second, and then this one that says LN. There's a little e to the x right above it. Okay, and then I'm up in my power position. Again, if you don't stay up in that power position, go ahead and use parentheses. Our interest rate was 0.05, and our time for this first one was 4. Okay, let's hit enter. And after 4 years, we're going to have $3,664 and about 21 cents, which means we earned, if we take off the original 3,000, we earned $664 in interest. Okay. What if we recall this? Second, enter. It's going to put that expression back in my calculator for me. But this time, let's go back and use our back arrow, change that 4 into an 8. and see what happens if we go another 4 years out. Now we have $4,475.74. So we earned the money in 5th grade, and by the time we graduate, we will have an extra $1,475. All right, let's go ahead and get those written down in our notes. So for the first one, we said our total amount was $3,664.21. After 8 years, we had $4,475.47. All right. So in this chapter, we have learned 4 different equations to model exponential word problems. Here's a table to identify the vocabulary to look for to clue you into which equation to use. So if they talk about exponential growth or decay, or use terms like populations increasing, growing, appreciating in value, those are all types of growth, and so we would use this exponential growth equation. If they talk about depreciation, decreasing, losing money, things like that, or losing value, now we're looking at exponential decay. Anytime we're dealing with interest that's not just a basic annual interest, then we have to move to our compounding formula. So we use this if it's compounded annually, quarterly, monthly, daily, weekly, things like that. As soon as you see the word continuous, you have to switch to this, what we call our PERT formula. P-E to the RT power, it spells PERT. So we call this our PERT formula. It's for compounding continuously. Okay, so let's look at 2 more examples here. It says a culture of bacteria starts with 30 cells and grows at a rate of 16% every hour. How many bacteria will there be after 7 hours? So this is a basic exponential growth equation. So we're going to use our growth model. Okay? So our total amount is our starting amount, 30 cells, times 1 plus our rate of increase, which was 16%. Again, we have to convert that to a decimal, so 0.16. And then our power is our time. Notice that time here is in hours, but they're asking us to find after 7 hours. So all we have to do is put a 7 in for our time. All right, let's grab our calculator. 30 times 1 plus 0.16 to the 7th power. And my calculator's back here somewhere. All right, 30 times 1 plus 0.16, and our power was 7. All right, so we will have 84.786, or about 85 bacteria. Okay. All right, our next example, it says the Smith family is saving up for a family vacation they want to take in 5 years. They put $1,200 in the bank that has an interest rate of 8.8% compounded monthly. How much money would they have by the time they want to take their trip? All right, so right here, compounded monthly. That tells me that I need to use this equation, okay? Compounded monthly. Any type of compounding other than continuous is going to be this formula. So we need P, R, N, and T. Our principal, we started with $1,200. Our interest rate was 8.8%. So again, converting that to a decimal would be 0.088. It's compounded monthly. Monthly, there's 12 months in a year, so our N value is going to be 12 times each year. And they said they wanted to take the vacation 5 years from now, so time would be 5. Okay, so the total amount of money that we're going to have, our starting $1,200, we have 1 plus our interest rate as a decimal, 0.088, divided by the number of times it's being compounded, and then our power has to be N times t. So it's happening 12 times a year for 5 years. So our power would end up being a 60, 12 times 5. All right, let's check our calculator again. All right, so we had 1,200 times 1 plus 0.088. We are dividing that into 12 chunks, and then our power is 12 times 5. All right, so when we head off for vacation, we will have $1,860.26. All right, I already forgot what I said. What was it? 1860.26. Okay, so today's homework, you're going to work on this compounding interest formula, and then also a review of all of the other exponential formulas.